Okay, yeah, that's the one I can talk about. Good. There's been a great deal of work recently trying to sort of verify a pretty much already accepted notion that the origin of the hydrogen that is seen in the M-cubed data and now the Cassini and epoxy data really derives from the solar wind. And I think that that's pretty much the potential that that hydrogen is coming from there is pretty much demonstrated. We got a paper out, probably one among many, Ichimura et al. In Earth and Planetary Science Letters, where we've actually taken some lunar soil and we've heated it up and then bombarded it with hydrogen and reproduced pretty much the same kind of curve that we had with unbaked out soil that had plenty of original hydrogen in it. You can bake it out and bombard it with deuterium, and you get a band over here which is shifted in terms of the mass of the isotope. So I think we pretty much have demonstrated something that really wasn't all that much in question in the first place, but it is good to nail it down. However, if you take a look at the distribution of the OH absorptions, and this is from a recent paper by McCord et al., where the latitude is here, and this is the depth of that 2.8 micron band. And this is the band that is likely to, due to some sort of OH, that is distinct from the putative 3 micron band, which they only really saw the lip of, and that has to be, well, it's kind of a complicated process to get these band depths. They really have to fit a black body curve to the M-cube data and then deconvolve from the residual at least 2 bands if they get 2. And that M-cube data stops about 3 microns. So they got problems being absolutely certain about the 3 micron band. But the 2.8 micron band, which is at least nominally due to OH, is pretty much sorted out. And looking at the latitudinal distribution from the McCord paper, you can see right away that what you are looking at there is not at all the production function, which looks kind of like this from the solar wind, where you've got protons impacting as the cosine of the zenith angle. But in fact, it looks pretty much like a mirror image of the production function. And so what this means here is that the process that you're seeing, the signature of the spatial distribution, reflects not the production of it, but the subsequent transport of a different population. Okay, the OH bands that you are getting from implantation of solar wind, very high energy solar wind, that population's got to be there. It takes a while for the hydrogen that is implanted there to work its way out. But that population actually would pretty much saturate even at the lunar poles in a few thousand years. So it would basically just be a totally uniform distribution. And the fact that you're seeing sort of an inverse of the production function tells you there's a population in here that is mobile, that is being moved around the planet. And the thing about that, when you have hydrogen or OH or whatever it may be that is migrating around the planet, it's going to be making ballistic hops that are much, much lower energy than the original impact that got the hydrogen embedded, implanted into the solar regolith. This stuff's going to be thermally accommodated to the soil at whatever point it takes off, and when it comes back down, it's going to sit. The best it can do, really, is to form sort of a chemisorbed OH on the surface, and we're sort of proceeding here with the understanding, with the expectation that we don't really yet have enough spectral resolution to be able to tell the difference between hydrogen that is implanted in rims, that's stuck in the glass, versus hydrogen-bearing species that are chemisorbed on a surface, where they would have more degrees of freedom, as just not clear, and spectroscopically you'd expect to be able to tell those apart given enough time and spectral resolution, but it's not clear we can do that. Instead, we're sort of treating them both as equivalent absorbers, and because we got a 2.8, we got a fundamental band here, you can sort of draw a qualitative relationship between the depth of that band, the residual depth of the band, and the weight percent of the absorber that's sitting there. This plot, whoops, that's not it, go backwards. This plot here is actually from Millikan et al., and they were looking at magnesium sulfate, where they've got band depth at 2.9 versus weight percent. But this and the specific numbers here, of course, are going to be different for all of the, for any species. However, the general shape of this is pretty much going to be correct, and at very small, over very small ranges at very small band depths, it's kind of a linear relationship. So we're going to kind of go forward with a qualitative analysis of what we might be seeing here, with sort of the assumption that we can use that, and that's something that's got to be, we've got to go back and beat on considerably more rigorously. Actually, I want to show one thing that is important here. This is the other plot of band depth, and this comes from the epoxy data, and I really haven't seen a more quantitative version of this. But McCord et al. Have looked over this, again, pretty carefully, and they're sticking with this notion that there is, in fact, a change, a decrease in the band depth, a loss of absorbers as a function of the solar hour angle, meaning that as the moon is rotating over the course of roughly 1 week, as you go from morning terminator to near noon, you're losing maybe half of the absorbers from the original population. Some tens of % of those things are going away. They're going someplace else. And that's can be combined with this notion that you've got two populations in kind of a very simple, there we go, a very simple model of what the consequences of that have to be, okay? So you've got a population of absorbers, and as I said, we're making the assumption that we can't tell implanted hydrogen from surface OH or whatever it is. And you've got a couple of different impacts here. You have a cosine of the zenith angle source, that's J1, and you have some time scale that is associated with diffusion of that proton out of the glassy matrix. Okay, that's going to be temperature dependent. It's a diffusion term. And then you have J2, which is the re-impact of all of the hydrogen-bearing species. And right now we're just sort of working, assuming we're just using protons here. That is the re-impact of ballistically launched protons from every place else on the surface that has them. And finally, you've got some time scale associated with the strength of the chemisorption bond and the vibration frequency, and every so often you know, depending on the temperature, again, this is a Boltzmann distribution, you exceed that energy and the thing takes off and it's come down somewhere else. Okay, and so there's a lot of stuff here that I actually do not know the values for is the problem, but we do sort of have this qualitative pattern that we're looking at, where as you go from, and this is a plot here of, go back. This is a plot of number density of absorbers in equilibrium. This is, we run these things out to equilibrium, and basically I'm doing two things here. This is just a matrix of what these qualitative patterns look like as you increase the bond strength that is associated with those surface chemisorbed units, or B, you increase the diffusive escape time. That's a different Boltzmann distribution. And what happens is that as you make these things increasingly difficult, you just get a function of H density that is dependent entirely on the latitude. As you make these things easier and easier to break, as you make the diffusion faster, as you make the bonds easier to break in the chemisorption, you start to see an hour angle dependency, okay? And so the point is, and what happens is the population of these ballistic, the ballistic population, let's call it that, rather than the implanted population. The ballistic population gets bigger and bigger until it's at least the same size as the implanted population. Okay, and that's kind of the condition that you need to have in order to see this hour angle dependency in these two populations. And so, pending a number of things that we're trying to do here, which is get some rigorous band depth plots versus solar hour angle. And I'm trying to get this out of the M-cubed data, but believe me, it's it's just one of those things that the uninitiated bumble with, and it's supposed to be done by now, but it's not. But what we're going to actually do is pull out rigorous band depths as a function of our angle, go back through the literature and see to what extent we can relate that 2.8 band depth to weight percent of H2O or OH in glassy matrices. And we want to try to firm up that quantitative band depth weight percent relationship, but the point is that you can come up with something that looks kind of like this, and to the extent that we have qualitatively matched what is observed in the M-cube data, you can use this pattern and the pattern in the M-cube data to determine the size of into this ballistically migrating population. And as long as, the bottom line is, as long as you've got this hour angle dependency and as long as it's fairly serious, then that population of migrating species is at least as great as the 10 to the 15, 10 to the 16 per square centimeter that you would get in the implanted population. And so some constraints on the total migrating population of H is going to be derivable from this numerically. And it looks as if it's going to be a sort of a substantial population. So chunk away on getting real numbers for all of these things, but that's the status right now. Questions? Bill? Yeah, hey, I wanted to ask you, the migrating population itself has an origin. Oh, thank you. The migrating population itself has its original origin from solar wind conversion from the surface. Correct. It's only available once the initial population has worked its way out of the glass, yeah. Gotcha. So there's an implanted population and a nomadic population. Yes. Yeah.
Do you have any thoughts on what the migrating molecule or atom would be?
It is certainly easier to get hydrogen alone back out of a glassy matrix, and under the assumption that you cannot tell OH on the surface from an OH on the inside, I would lean towards OH. I lean towards hydrogen as the migrating species, but of course there's you can check that against things like the expected ballistic trajectory and ionization of hydrogen and OH. And both of those things can be factored into calculating J2, that second flux of ballistic population. And one of them will match better than the other, I bet.
Thank you, Aaron. Okay, let's thank our speaker again.